One question we haven't really addressed is when the central limit theorem says you need a large number of draws before probabilities for the sum start looking normal. What do we mean by large? We've had a few hundreds and the approximations have been fine. Sometimes they work for about 30 and you have a probability distribution tool in your online text which you can use to play around with distributions and see how many draws you need to get to normality. But is there any kind of cutoff? How does that work? Well, there really isn't. And to give you an example of what goes on, let's take a number of draws that's really on the face of it seems very large. 1,000 trials, success-failure trials with chance 1 in 1,000 of success on a trial. Now 1,000 is large by anybody's standards. What we're going to do is we're going to look at the number of successes in these trials, and the probability distribution for the number of successes is, well, the number of successes in a bunch of trials. Yes, of course, that's binomial. So we know the exact distribution. It's binomial. N is 1,000. P is 0.001. I'm just writing it so that I don't have to carry the fraction around. Fine. Now, binomial probabilities involve large combinatorial terms, large powers of fractions. So let's see if we can get a bigger picture. The number of successes in these trials can be modeled as the sum of 100 draws. Now from which box? Chance of success is 1 in 1,000, so 1 out of the 1,000 tickets is a 1, and the remaining 999 are zeros. So what do I expect the number of successes to be? Well, it's the expected sum of the draws, which is the number of draws times the fraction of ones in the box, and that's 1. We expect 1 success, no big surprise. We're running 1,000 trials, the chance of success is 1 in 1,000. The standard error does need a calculation. Square root of number of trials times probability of 1 times probability of 0. And look at that. I deliberately kept all these decimal places. I wanted you to see how close it is to 1. We're saying, essentially, that we expect to get 1 success, give or take 1. So is that distribution going to be roughly normal? I mean, the theorem says you've got a large number of draws and you're looking at probabilities for the sum, so should it look normal? Well, what's the variable? The variable is the number of successes. What is the smallest that can be? That's 0, that's right. 0, 1, 2, 3, and you've got an expected value of 1, give or take 1. Well, if I go 2 standard errors below the expected value, I'm at a negative number of successes, and this is most unfortunate. This cannot be. And so, by a kind of assessment that you did back in Stat 2.1x, you know that this distribution is not going to be normal. So, what is it then? Well, let's see. It's a binomial distribution, so we can simply plot the histogram, and there it is. Not normal. 1,000 trials, chance 1 in 1,000 of success on each trial. On the horizontal axis, I have the number of successes. The expected value is 1, give or take about 1. Now, these two bars look identical, but they're actually not. This one is a tad taller. I think they're equal to the 3rd decimal place, if I remember correctly. So there's a high probability of getting no successes, 1 success, 2, 3, 4. How would I have known ahead of time that I shouldn't go past 6 here drawing? Well, we calculated that the expected value was 1 and the standard error was 1 as well. So what does Chebyshev say? 1 plus or minus 1 standard error, 2 standard errors, 3 standard errors, 4 standard errors, and after that there's really not much, no matter what the shape of the distribution. And that's what told me, go up to 6, but no further. In theory, it goes all the way out to 1,000. That's how many trials there are, so that's how many successes I could have in theory. but the likely successes are in the range 0 through about 5. So, can't use the normal approximation for this one. So what do? Well, you think about why you can't use the normal approximation, and the reason you can't use the normal approximation is that the probability of heads is so small, the probability of success is so small, that the number of successes is actually going to be rather small. The histogram is all squished up near 0. That means there are very few bars and they're all near 0, so how do I calculate the probability of this? Exactly, using the binomial formula. It's got a 1000 choose 0 in it, but 1000 choose 0 is just 1. There's only one way of choosing nothing out of 1000 objects. 1000 choose 1 is 1000. There are 1000 ways of choosing one object out of 1000. 1000 choose 2. Cancel the factorials and you will see that you have 1000 times 999 divided by 2. These are easy calculations that you can do on a hand calculator. So if you find you've got a binomial histogram and the normal approximation is not working out because this thing is centered, or its balance point is very close to 0, just find the exact probabilities. So the moral of this story is that while 1000 draws seems large, what you are drawing from has an effect. The box with 1 1 and 999 zeros is so lopsided, its distribution is so uneven, the bar at 1 is tiny compared to the bar at 0, that 1000 draws are, forget that, not enough for the central limit theorem to have started working yet. You need even more draws than that for the central limit theorem to work. Shall we try? Oh, why not? What if we made 10,000 draws from the same box? Then how many successes would we expect to get? Well, it would now be 10,000 times 1 in 1000, and we'd expect 10. No surprise there. And the standard error? 10,000 times chance of 1 times chance of 0 square root, and that's 3. So 10 give or take 3, Suddenly I can go 2 standard deviations, 2 standard errors below average, maybe 3. So is this normal? Well, it's a binomial histogram. I've got a decent computer. Let's just draw the thing, shall we? There we go. Very close to normal. The same coin, very biased, chance 1 in 1000 of giving you heads. But now lots and lots of tosses, 10,000 tosses, and the distribution of the number of heads is getting really close to normal. I see a little skewness here, but you can see that as you increase the number of tosses, the normal approximation will get better. So what is it that you look out for? It will take you a long time to achieve normality, by which I mean it will take lots and lots of draws before the probabilities for the sum start to look normal, if what you've got inside your box is not pretty. And one of the ways it may be not pretty is that it's quite far from symmetric. You saw one example, 1 1 and 999 zeros. You could have something with a very long tail. When you start with these distributions, it takes lots of draws before you get to normality for your probabilities for the sum. Equally, if your histogram of the numbers in the box has gaps in it, if it's a nasty thing, then it'll take a lot of draws. And I know people are saying, well, how many draws? I don't know. It depends on the box. So, from a practical perspective, what I would suggest is this. If you are using the normal approximation for the sum of the draws, you feel like the number of draws is large enough, calculate the expected value and calculate the standard error. You're going to have to do that anyway if you're going to use the normal approximation. Then just go 3 standard errors on either side of your expected value and see whether you're hitting nonsense. right? Whether a positive variable, suddenly you're hitting negative values, or whether, it's a percent and you're getting numbers that are bigger than 100%. If you are getting nonsense, don't use the normal approximation. And if your numbers are within a physically possible range, go ahead. You have to be aware that any approximation might be off. But with the techniques that you have at your disposal, this is the best advice that I can give you. With a little more computer expertise, you might be able to simulate and get a better sense of what's going on. You can, of course, always use the probability distribution tool from your online textbook to do some checking if the contents of the box are simple enough. But otherwise, just try this ballpark check. It's a good idea to try it. It's not always foolproof, but it's better than not trying anything.